crashed recently, the
Well,
private?
the one was detonated on purpose before it got over civilian population. So there was a problem.
But I mean, I don't.
With the rocket originally, so when it took off, they blew it up.
Right, but I mean, it wasn't like the plan was to blow it up from day one, though.
The plan was when whatever faltered.
Yeah.
Before it got over, like, and killed them.
Sure.
They blew it up.
Yeah, yeah, but that was disappointing. And then it sounded like the other one was a pilot error, right? That,
I think we should hold judgment. They said 9 seconds.
yeah.
But when you say 9 seconds, yeah, that 9 seconds is a really big deal when you talk about when you're
Oh yeah.
But I refuse to be like, there was not one person sitting around since they have so much data collection happening.
Mm.
I refuse to believe somebody was like, yeah, go ahead, John.
Oh, sure, yeah,
Pull that lever,
yeah.
like.
One would hope, yeah. But it's one of those things. It wasn't really even on my radar to be watching this thing. But as soon as you hear it happens, it's a major bummer. I mean,
there was a piloted.
Well, and one of the guys died.
Virgin Galactic.
Yeah.
Old Bronson, the billionaire.
Yeah.
Was like, I want to go to space, so he bought like Space One, and they're building to go to low orbit space.
The unmanned one blew up.
Yep, and then the other one blew up too.
Yeah. Well, it pulled apart. It really didn't blow up.
No, I don't know the
There was
details.
one,
It
the
ended
one
very
that
badly.
was on the pad, right?
Yep.
And that was to go to the space station.
Oh, yep, that's right.
And so something about how much water, like per gallon or something like that cost, because they were sending water up there.
Oh God, yeah.
It's like
God.
4,000 something.
Yeah.
$4,000.
You just got to remember, progress demands sacrifice, kids.
Yeah.
Well, yeah, but it's just too bad. I mean, I was, I don't know.
Let's look at all the experimental planes and all the pilots that died that you never got to hear about.
Yeah.
But it's private, and they're like, oh, it's costly, and you're like, oh, nobody ever remembers Columbia here? Guess I'm just by myself here.
No, I know.
So I know I look at space every day.
You're a space geek?
Well, not space geek, I just find it extremely interesting.
Yeah.
And I am going to put my name in every day for that win a trip to go to space.
Okay. No, I applied for Johnson Space Center astronaut school. I got denied. Health reasons.
I also almost finished my Mars One application too. Almost.
Yeah.
I was like, what?
Yeah, no, it's a weird sport. Okay, guys, here's a solar theory. No, solar theory. We're gonna do thermal. And here's what I want to get the point that I want to reiterate about any engineered system. Do you guys remember off the top of your head what the two variables are that get multiplied together to get power? So what we're going to attempt to do now is just draw a bunch of ideas together so that you're not trying to memorize all this stuff all the time. I mean, power equation. So in electronics, so let's do it this way.
So P equals work over time. P equals current squared times resistance. P equals voltage times current. P equals voltage squared divided by resistance.
Yeah. So in electronics, how do you get? What do you multiply what by what to get power?
So you can multiply voltage times current.
Voltage times current. Perfect. V times I. Mechanically, for linear motion, what is it?
Work over time.
Power is work over time, but what two things do you multiply each other by to get power? You can't divide here. What's that?
Watt and time.
Watts and time. No, power is measured in watts. So mass times velocity is momentum, so that's not power. Good guess. I'll give you a hint though. Velocity is one of the components. So I'll put little v here for velocity.
Well, there'd be time in there too, correct?
Oh, there's got to be time. Yeah. First of all, the dimensions of power
Work over time.
is the dimensions of power is mass times length squared over time cubed. It might look kind of weird, like, okay, what part of voltage or current is mass? Well, there's a there's a definition of voltage and current that tie it back to mass, length, and time.
1/2, is it the 1/2 equation?
1/2 mv squared is energy, so that's not power either, but keep going with it. What am I going to multiply velocity by to get power in a linear mechanical system? Think about a football player, a lineman pushing on another football player, and you might say that is a very powerful lineman because he's moving at a high velocity and he's pushing.
Weight, mass?
Yes, he's pushing mass and he's using force to do it. Thank you. So it's force times velocity. When you multiply force and velocity together in a linear system, you get power. Okay, next one. Mechanical rotational. Power equals what two variables? What are you going to multiply? Because in this case, in a rotational system, there's no velocity component. It's not moving anywhere. What's it doing instead? It's rotating at some angular velocity, omega, funny looking W, omega.
This is kind of like to the wind turbine, right?
It's to the wind turbine, absolutely.
Like tip speed would be.
Torque, thank you, it's torque, yep. You guys are all on the same team here, by the way, it's not a competition. So what ends up happening is, so here's the next one. Mechanical thermal, which is where we're going. I have a purpose here. Waiting for it, here it comes. So what two things am I going to multiply each other by to figure out how much thermal power I have moving through my system? There's probably more than one answer, but the bottom line is it has to work out such that we come up with this funny looking thing, mass times length squared over time cubed. And you might say, well, where is that? Well, because force is mass times acceleration, which looks like that, and velocity is distance over time, looks like that. That's how you get your linear. Torque is, torque is force times distance, so it's kind of weird, but torque and energy have the same dimensions. So torque is mass length squared over time squared, and angular velocity, just measured in hertz, it's just 1 over time, gives you your power. So somehow we got to figure out thermally how to get at a thermal power equation, because that's what's going to be important to Nicky Robinson's system. That's what's going to be important to Dustin's system too. He's going to want to know how much heat am I pumping through my system. It's going to be important for your geothermal too. How much heat's coming through it. So let's think this thing through. What's something you might be able to measure in this solar thermal exchanger we've got here?
The area that is.
We can measure the area. Yeah, that's.
Yeah, the in-out temperatures.
We got the temperature. And what area are you talking about here? Just.
The absorption area or the sun's hitting.
Yeah, you do have this area. What do you want to call this? Area of collector. But I'm going to focus more on this guy. This is the area of the duct, because that's where the heat transfer is actually occurring. It's getting shot through that duct. So let's start listing some variables out here. We got temperature, and I apologize. I used a big T for time. Normally you'd use a little t, but I used a big M, a big L, and a big T because that's also the convention for dimensions. When you're writing it out in an equation form, you would normally use a little t for time. But here, I'm sorry, I'm using big T for temp. Sometimes in the textbooks, and it might even be, well, in fact, it's sitting right here in your solar thermal book. The authors use theta. Do you see that in the textbook? So I'll write it this way as a little reminder. Ding. Theta equals temperature. We mentioned area. This is going to be the area of the duct. So we can measure temperature, for sure, with our thermometer. We can measure the area of the duct, just put a ruler or tape measure across it. What else might we measure?
Velocity of the air moving through.
Yes, yes, yes. Velocity of the air moving through. Okay, now, we're going to do some dimensional analysis here and see if somehow, have you guys done dimensional analysis with Kearns much? So one thing Brian Kearns told me the other day is like, you know, Brad, I'm really impressed with the knowledge that a lot of the 200 level students are coming into my classes. So I've tried to hit, I mean, you've seen me do this stuff before in 101, 102, but it's not a surprise. What we're going to try now is to figure out how to combine these three variables, temperature, area, and velocity, and come up with power. And this is a critical skill for energy technology. How the heck are we going to do it? Okay, what are the dimensions of area? Well, that's just length squared. What are the dimensions of velocity? Well, we know that's length over time. Now, what the heck are the dimensions of temperature? I don't want to go too deep down the rabbit hole here, but let's just go back to the gas law. So we got P, V equals N, R, T. That's pressure, that's volume, that's how much gas you have, it's how many molecules in the system. R is there as a constant to make everything hunky-dory, work out with units, and T is temperature. So, pressure is actually, when it comes down, right down to it, pressure is energy per unit volume. So this is energy times energy. The ideal gas law is an energy equation. So what is temperature? I'm going to write it like this. Temperature equals PV over NR. Like I said, R is just there for bookkeeping purposes. So we can just, so I'm going to write it again, equals PV over N. I already told you that pressure times volume is energy. So what that is, temperature is just energy per particle. Fundamentally, that's all temperature is. It's how much, it's an intensive variable, just like density is an intensive variable. It's an averaging system because there's no way you're going to build a machine that's going to tell you how much energy every single atom has. You're just averaging them out. You know that they're bouncing around off of each other. So that's really fundamentally all that temperature is. So let's go back to this heat equation and say that we know that E equals C sub P M T. That is how much energy there is in a chunk of matter. Now, in the case of the solar thermal air system, we got to use the, why can I never remember the name of this thing? The, I think it's just called the heat coefficient. Thermal capacity. Dang it, I always forget. Getting old and leaky. I want to know the name for C sub P. Heat capacitance. Here we go. Heat capacity. Air properties. Engineering toolbox. That's a good one.
Yeah, on there.
Specific heat capacity. There you go. Sorry. Specific heat capacity. Now, why the word specific there?
Does it change the temperature?
Say again, well,
Well,
it does change the function of temperature, you're right, but it's the heat capacity per unit mass. So we're going to need to know like the mass of the air in the system. So we can see that it's kilojoules, so it's energy per unit mass per Kelvin. And for air, lucky for us, it's 1. 1 joule, so let's do that. So for air equals 1 joule, well, yeah, let's use kilojoules. It's 1 joule per gram, or it's 1 kilojoule per kilogram Kelvin. All right, yep, good. Now, so what we can also do, and then the mass we'll just have to figure out. Now, the mass is going to be the, probably the best way to get mass is just volume times density. So let's rewrite it like this. Temperature equals energy over C sub P. Mass is what the heck is mass? What did I just say it was? Density times volume. Thank you. Good. Yeah. So now we've basically redefined temperature in terms of energy, and we know that. Well, this is going to get kind of nasty here for a second, but let's see if we can do this. I'm going to rewrite it up here so I can kind of cheat a little bit. T equals E C sub P rho V. And remember, that's a big V for volume. This guy right here is a little v for velocity we wrote before. Okay. The other thing that really needs to be stressed here is that in every single one of these equations, and I wrote them this way purposefully, the first variable is what's called the across variable. And the second one is what's called the through variable. You might have heard me talk about this before, but here's where it counts. So the across variable is like, think about it, you have voltage across two terminals. You have force across the ends of a chunk of rope. You have torque. Torque's a little bit weirder on a cross, but you can think about like you torque one end of the shaft and the other end is getting that same torque. In terms of current, this is pretty obvious. Current flows through the system. Velocity is flowing through the system, and your angular velocity is sort of moving in a circle. So we need to figure out now what's our across variable and what's our through variable. And first of all, what's the through variable? What's going on with the system?
The flow rate of air?
It should be the flow rate. Yeah, it definitely should be the flow rate. Now, the question is whether we should use velocity or if we use the area or if we use some combination thereof. So if we multiply the area times the velocity, let's just grab those two guys together, we're going to get a cubic length over time. Now that's just the volumetric flow rate. That's going to be how many cubic meters per minute. So if we had a way, and Troy Savage had a nice little system to measure the velocity. If we can get a hold of that, maybe we will. To measure the velocity through a duct. It could even be that Zandy Sievers has a duct blaster so we could measure the velocity. But let's just assume that we can measure the velocity. And we already know the area. That's going to give us the volumetric flow rate. Now, the only thing we have to do is figure out, so I'm going to, so let's just call this the through variable for our system. Kind of run out of room here. And I'm going to call it, gosh, volumetric, let's just call it this. Let's call it big V dot. Because we all know that big V is volume, and the dot just means per unit time. So this is going to be big V dot right here. All we need to do now is figure out how to get, what do we need? We still need mass somehow. We still need, we need 1 over time squared somehow. And the last thing we need, I think we actually need length in the numerator, don't we? Because we've got length cubed in the denominator, but we know that every one of these power equations has to come up looking like this. Power has to be mass times length squared, not cubed, over time cubed. All right, so I'm going to take a quick commercial break because I don't know exactly how this comes out. I gotta figure that out. But once you guys puzzle over it for a little bit, I'll do the same, and then we'll figure out exactly what that across variable needs to be. Whew.